Hi, I'm Miss Hearn. Let's get started. In this video, we're going to talk about common argument forms. But before we do, we have to talk about statements that are related to conditional statements. So when we take a conditional statement, which is an if-then statement, if something happens, then something else happens, and we rearrange or change it in certain ways, we have a special name for each of those ways. In all of these, I'm going to be referring to the original conditional statement being if P then Q. First change I'm going to make to that original conditional statement is what if we switched the components? Remember, the components are the P and the Q. They're the smaller statements within the larger if-then statement. So if we switch those and we put the Q as the hypothesis and the P as the conclusion instead of the other way around, we call that the converse of the original statement. So the converse is where we switch components. The inverse refers to when we take, again, that original statement. I'm referring back to the original conditional statement. If we take that statement and we do not change the order, but what we do is put a negation of each of the individual components. So if not P happens, then not Q happens. Or another way of saying that is if P doesn't happen, then Q doesn't happen. So when we negate the components without switching the order, that's called the inverse. And finally, and most importantly, if we make both of those changes, it's called the contrapositive. So if we both switch the order and negate the components, so we have if not Q, then not P. If Q doesn't happen, then P doesn't happen. That's called the contrapositive. This one's going to be the most important to us in the work that we do today. So let's practice with this idea. In example 1, consider the conditional proposition, if California is in North America, then Florida is in Africa. So first of all, I want to point out that California is in North America. That's true. And Florida is definitely not in Africa. That's false. So this fits the if true then false truth pattern. And we've discussed that this is exactly and the only time that a conditional statement is considered false. When you have true implies false, I like to say the promise is made and then broken, then that's the only time you get a false. And we practiced that in the last lesson. So in this lesson, we're going to take this original conditional proposition or conditional statement, and we're going to create new statements that are related to it, the converse, the inverse, and the contrapositive. Now remember, the converse changes the order. We switch the order of the hypothesis and the conclusion. The inverse keeps the order the same, but it negates the components. It negates the hypothesis and negates the conclusion. And the contrapositive makes both changes. It both switches the order and negates the components. So the converse would be the same wording, but with the first and second components, the hypothesis and conclusion, flipped. So we could say if Florida is in Africa, then California is in North America. That's the converse of the original conditional because the order is flipped. Now let's write the inverse. So the inverse is where you keep the order the same as the original and you negate the component. So we're still going to have the California's in North America part coming first, but we're going to change it to it's not in North America. We're still going to have Florida is in Africa coming second, but we're going to change it to Florida is not in Africa. So we still have the if in the front. California isn't in North America, then Florida isn't in Africa. Okay, and then now the contrapositive makes both changes. So we need the Florida part to be at the beginning and the California part to be at the end, and we need to negate both. So if Florida isn't in Africa, then California isn't in North America. All right, so before we move on, in order to give us a glimpse into how these statements might relate to the original, remember we learned that statements are equivalent if their truth values are the same in the same situations, and they are negations of each other if their truth values are always opposite. Now, what I'm about to do is not going to prove whether any of these are equivalent or opposite, because we're only looking at one scenario, but we could at least take a guess, right? So we'll have a little bit more information. So for part A, let's look at the truth value. We know that Florida is in Africa is false. We know that California is in North America is true. This means that the converse gave us a false implies true statement, which makes sense because the order is reversed. But remember, the only time that we get a false is when we have true first as the hypothesis and then the conclusion is false. So in the case of this truth pattern, in the case of this truth pattern, we actually get a true. Okay. Anything other than true implies false is going to be true for the conditional. All right, now let's look at the inverse. The inverse, we said California isn't in North America, which is false. And we said Florida isn't in Africa, which is true. So once again, we get the false implies true truth pattern, which we know to be true. Now let's look at the contrapositive. So for the contrapositive, we have Florida isn't in Africa, which is a true statement. And we have California isn't in North America, which would be false. So we get the true implies false truth pattern, which we know to be false. So notice that the only one that could potentially have the same meaning as the original statement could be equivalent because it has the same truth value, at least in this one situation, is the contrapositive. The contrapositive and the original statement both had a true implies false truth value. But how can we know? So again, I suspect from this information, it seems like the contrapositive could possibly be equivalent to the original statement. So we're asking ourselves, is the contrapositive equivalent to the original statement? Well, one way you can think about it is in words. But don't worry, if you don't follow what I'm about to say, I'm going to prove it another way. So we're saying that if California is in North America, that forces Florida to be in Africa. But the contrapositive says if Florida isn't in Africa, then California isn't in North America. So suppose that we thought the conditional statement's true, right? We believe that if California is in North America, then Florida has to be in Africa. Then if I tell you that Florida isn't in Africa, wouldn't that mean California could not have possibly been in North America? Because that would have forced Florida to be in Africa. So it does appear that these two statements are consistent, at least, with each other. But how can we be sure that they actually have the same meaning? So there's something called a truth table, which you can use in order to list all the possible scenarios and then analyze the truth value of a statement in each of those scenarios so you know exactly when it's true and exactly when it's false. So I'm going to make a truth table that compares the truth values of the original conditional if P then Q to the truth values of its contrapositive if not Q then not P. So there are only 4 possible scenarios. Scenario A, both components are true, so P and Q are both true. Scenario B would be only P is true, but Q is false. So we have a true and then a false. You see the headings for P and Q, so I'm just using the description of the scenario to fill in what their truth values would be. The next possible scenario is only Q being true, right? So it's possible Q is true, but the original, the hypothesis was false. And then it's also possible that both components are false. These 4 scenarios are the only possible scenarios. So let's see what happens in each with the statement if P then Q. Well, we know that the conditional if P then Q is only going to be false when we have true implies false. True implies false gives you a false. So in the first scenario A, do we have true implies false? No. We have if true, then true. So that means this one would give us a true. Anytime that both the components are true in a conditional statement, you're going to get a true. Now let's look at scenario B. If P is true and Q is false. So we have if a true, then a false. Well, we know that's the only time we're going to get a false, so that one's going to be false. Now let's look at the truth pattern of the third scenario, only Q being true. Well, that would mean that the hypothesis is false and the conclusion is true. Now, the only way we get a false is if we have it reversed, so this is actually going to be true. And then what if both components are false? Then we would have false implies false. And again, the only time we get a overall false statement is when we have T arrow F, which is not what we have in this truth pattern, so this is considered true. So the truth values that occur are true, false, true, true for the original conditional statement. Now let's analyze its contrapositive. So it's contrapositive if not Q, then not P. Let's see how that's going to go. So if not Q, then not P means, in this case, we have both components being true, right? So a not true implies not true. Or in other words, false implies false. Well, we know that for a conditional, it's only going to be false if we have true arrow false. So this one's going to actually be considered true. Okay, and then what if we had not, and then Q is false? Look over here, we're looking at the second column. It's easy to think we're supposed to do the true first if you're not looking at this correctly. Remember, that means P is true and Q is false. So we would have not false implies not true. Okay, but not false means true, and not true means false. So this would be the true implies false, the only time conditional statements are false. The promise was made and then broken. And then the next scenario is when only Q is true. So that would be a not true implies not false, where Q is true and P is false. Well, the negation of a true is a false, the negation of a false is a true. So this would be a false implies true scenario, which is true. And then finally, if they're both false, we would have not false implies not false. which is true implies true. And again, that doesn't fit the true implies false scenario, so it has to be true. So for the contrapositive, we got true, false, true, true. So notice that these two statements, the original conditional and its contrapositive, have all the same truth values. This means that they are equivalent. So this chart demonstrates that the conditional, if P then Q, and the contrapositive are equivalent because they have all the same truth values in all the same scenarios. Which, remember, was the definition of what it means for two logical statements to be equivalent. That's something you're going to need to know for your test on the module. All right, so what we're saying is anytime you have a statement, if P then Q, you need to recognize that it means the same thing as if not Q, then not P. If P happens, then Q is guaranteed to happen. So if Q doesn't happen, it must have been that P didn't either. So let's practice writing conditional statements or conditional propositions and their contrapositive. So here's a conditional statement. The team will win only if they practice consistently. Now, we have talked about different wording for the conditional, and we've talked about a chart that shows us, let me see if I have it here. Here we go. We've talked about a chart that shows us whether the hypothesis is at the beginning of the statement or at the end. All of these statements are equivalent to each other. This statement, P only if Q, this statement form is what we're looking at right now. Notice that the hypothesis is at the beginning and the conclusions at the end. So if we want to write it in if P then Q format, we just keep the order the same and change the wording a little. So for the only if, we know that this is the, I'm going to stop writing in red. For the only if, we know that this is the hypothesis and this is the conclusion. And I always refer to P as being the hypothesis and Q being the conclusion, but that's not necessarily the case. That's just what I'm using in the chart. But anyway, so that would mean that we're going to have if the team will win. So if the team wins, I'm going to say, you can always change the verb tense and so forth. Then what? Then they practice consistently. Okay, this is the original statement, just written in if-then form. So I have not even addressed the contrapositive yet. Okay, now we're going to write it as its contrapositive, which we have just proven is really logically equivalent. It has the same meaning ultimately. So we're going to say if not the conclusion, then not the hypothesis. So we're going to say if not, if they don't practice consistently, then the team does not win. which makes sense because we know that if the team won, they would have been practicing consistently. So if they haven't been, they must not have won. You see how that works? Okay. So, it's also important to note that while the original conditional statement was equivalent to its contrapositive, because it had all the same truth values, it actually does not have the same truth values as its converse or inverse. So it is not equivalent to its converse, and it's not equivalent to its inverse. All right, now we're on to the next topic. The next topic is common valid argument forms. We've already discussed how to use an Euler diagram such as this one to determine if an argument is valid or invalid. But wouldn't it be nice to know certain common situations where you don't have to draw this picture? You can just know that it's a valid argument. So let's read this argument. It says, everyone who studies math gets a headache. You study math, therefore you get a headache. This actually is a common logic pattern known as modus ponens. So what we see in modus ponens is, let me erase this red. We want to be looking at the, other part of the screen. Okay. So is the pattern all P's are Q's, P happens, therefore Q happens. And remember, there are a lot of different ways to write conditional statements, and one of them was the all P's are Q's. So that is actually an if P then Q statement. So what we're saying here is if P happens, then Q happens. And we know that P happens. So therefore, from the original if-then statement, we know that Q happens as well. That information is printed in your notes right here. If P happens, then Q happens. P does happen, therefore Q happens. Okay, so anytime you can make, without changing the meaning, you can write an argument in this format, you know that it's valid. You don't have to try to figure it out with an Euler diagram, which is nice. So let's look at this example. So in example 2, we were asked to identify the argument we know to be valid because it follows the modus ponens logic pattern. So let's try to identify the logic patterns. Remember, we are looking for a certain pattern, which is that the first statement has got to be in the form if P then Q. And then the second statement has to confirm that P happens. And then the third statement is the conclusion. And so it says, therefore, Q happens. Okay, so let's see if we can identify patterns of each of these statements. So in part A, we have, if today is Tuesday, then tomorrow is Wednesday. So we have the P implies Q. Again, if today is Tuesday, so P would be the today is Tuesday, and tomorrow is Wednesday. Okay, so we have that. That's the first statement. That's done. But the second statement is tomorrow is Wednesday. Is that P or is that Q? That is actually saying that Q happened. And that is not what we're looking for. We want to see that the hypothesis happens, not that the conclusion happens. So this could be valid or invalid. We're not going to discuss that because that's not what we're focused on right now. But it doesn't follow the modus ponens logic pattern. So let's look at option B here. So I'm going to erase this stuff, okay? Because we're going to focus on B. So B says calling the paramedics is necessary when someone is having a heart attack. Okay, so this one is not written in if P then Q form. So to know what is the P, the hypothesis, and what's the conclusion, we need to refer to this, the sentence pattern that has the keyword is necessary for. So let's go back up to this chart, which will be provided on your test. Okay, remember Q is necessary for P. The beginning of the sentence is actually the conclusion, and the end is the hypothesis. Okay, so let's label it that way here. So something about calling the paramedics is going to be our Q. And our P is someone is having a heart attack. Okay, so now we've identified that we do have a conditional statement of the form P implies Q. It's not written as if P then Q, but that's okay. It's equivalent to it. So at least we know what our hypothesis and our conclusion are supposed to be. Now the pattern we're looking for up here, we want P to be the next statement. So let's see if it is. So the next statement is someone is having a heart attack. Okay, which one was that? Well, that was P. So the second statement is that P is happening. And that's what we wanted to see. Okay, so far we're good through the first two statements. Now let's see if it has the right conclusion. So the conclusion is, oh, I should put a P here. Okay. The conclusion is therefore the paramedics are called, which is Q. Okay, so the third statement, the conclusion is Q. So this does fit the pattern. So B would be valid, first of all, by the modus ponens logic pattern. If you notice that it follows if P then Q, P happens, therefore Q happens, then you know you have the modus ponens logic pattern. Okay? Now I'm pretty sure, because I said identify the argument, that there was only one of these that turned out to be, but let's check the others just to see if they are or not. So I'm going to erase this and look at the next part, C. So in part C we have it is raining only if there are clouds. Now anytime you see the word only next to if, think of it as a then. Okay, it changes the word, it changes the meaning of if to have the word only next to it. So think of this as if it is raining, if P, then Q, there are clouds. So we have established the first part. We have an if-then statement. We know what our P and our Q are. What then would be the second part? Well, the second part is there are clouds. So this is saying that Q happened. Okay, but again, that is not what we're looking for. We're looking for P to happen. So this definitely doesn't fit the modus ponens pattern. It could be valid, it could be not valid, could be invalid, I should say, but that's not what we're here to determine. We would have to use other methods because it's not modus ponens. Okay, now the next one, part D. So for part D, the course is challenging if it is mathematics. We have the keyword if right in the middle of the statement without the word only next to it. Just to remind you, this is the Q if P pattern, when you just see if in the middle of the sentence and no only next to it. This means that the conclusion is at the beginning again, and the hypothesis is at the end anytime we see this pattern. So the P, the hypothesis, would be it's a math class or course, and then this guy is going to be our conclusion, Q. In other words, this is the same as saying if it's a math course, then it's challenging. Okay, so we have established our conditional statement as the one of the premises, and now the next one, it is not challenging. That would be it's not Q. So the second statement is not Q. Q didn't happen, in other words. Again, we're just looking for P to happen, so this is not going to fit the pattern. So that's why the only one of these four statements that fits the modus ponens logic pattern, and therefore we could say is valid without any further investigation, would be option B. All right, let's look at another logic pattern. So this one is called modus tollens. Modus tollens starts out the same as modus ponens, so we still have all P's or Q's, but then we say Q didn't happen. So in this Euler diagram, you see all P's or Q's, so that means that the P circle is inside of the Q circle. But then we say that Q didn't happen. So in other words, that X is not a Q. So it has to be outside the Q circle, which means that X is not a P either. So the conclusion is P didn't happen either. Okay, another way, again, to write this is if P happens, then Q happens. But Q doesn't happen. Therefore, P doesn't happen either. Do you recognize that pattern? So notice that this is actually equivalent to the contrapositive to say Q doesn't happen causes P not to happen. So actually, the reason why modus tollens turns out to be a valid argument form is because it contains the contrapositive. But you don't need to know that. All you need to be able to do is to recognize the pattern. Okay, so I have one for you to work. I would recommend that you pause the video and try to figure out which one of these arguments we know is valid by modus tollens. So I'm not asking you to identify which is valid and which is invalid. I just really need you to identify which of these statements fits the modus tollens logic pattern. Being valid follows automatically from that. So again, please pause the video and try to rewrite each of these statements as we did in the previous example, and just see how you did. Then push play and watch the solution. Okay, so let's see if you got it right. So in part A, we have if today is Tuesday. Oh, before I do that, let's remind us what we're looking for. So we're looking for a conditional statement to be our first premise, the first statement. And then the second one to say that Q didn't happen, that the conclusion didn't happen. And then that means that the third one, the conclusion to the argument, is that P could not have possibly happened either. Okay, so in A, P is today is Tuesday and Q is tomorrow is Wednesday. So that being the case, that P is Tuesday and tomorrow's Wednesday is Q, then today is not Tuesday would be contradicting P. So this would be not P. Now I can stop right there. It doesn't even matter what the conclusion is because I was looking for the second statement to be not Q. So that doesn't fit. So let's look at the, or let me jot that down in the notes below. So for A, we had the first statement was P implies Q. The second statement was not Q. So we know that's not going to be the modus tollens pattern. Oh, excuse me. It was, sorry, it was, the second statement is not P, not Tuesday, so that did not fit the modus tollens pattern. Okay, for part B now. If no one is having a heart attack, no one is having a heart attack would be RP. There is no need to call the paramedics would be RQ. No one is having a heart attack. So, by the way, so our first statement is P implies Q. We're good there. So, but no one is having a heart attack means that P happens next. So the second statement is P again. But we're looking for not Q, so that's not going to work. Doesn't fit the pattern. Okay. It is not raining only if there are no clouds in the sky. Remember, this only if is like a then. So P is it's not raining, the hypothesis, and Q, the conclusion is there are no clouds. All right, so far we have our first statement is P implies Q. And then we're looking at the second statement. Now, the second statement is there are no clouds, which is the same as Q. So we're saying Q happens. And again, we don't want Q to happen. We need not Q to happen. All right, so that one doesn't fit. Now let's look at part D. Part D says the course is challenging if it is mathematics. Once again, we have an if in the middle of the statement. So this is a Q if P pattern. So the hypothesis is actually the end of the statement and the conclusion's at the beginning. So we have P implies Q. Sure, we could write it as Q happens if P happens. The arrow would have to go backwards, so we don't usually do that. Okay, so we just think of it as it's an if-then statement. If it is a math course, then it is challenging. Okay, so we have that. Now the next statement, that was supposed to be statement 1. Let's fix that. The next statement, statement 2, is it's not challenging. Not challenging is not Q, which is exactly what we're looking for. So far, so good with that. Now let's see what the conclusion of the argument is. It's supposed to be not P. It says, therefore, it is not a math class. So this was not Q, and yes, this is not P. So D is the correct answer. Okay. All right, one more argument form that I want you to learn, and this is my favorite argument form. I think everyone should be familiar with this argument form. It's called reasoning by transitivity. So it says that if you know all P's are Q's and you know all Q's are R's, then that must mean that all P's are R's. You can see this in this diagram. The P circle's inside of the Q circle, representing all P's are Q's. And the Q circle is inside of the R circle, representing all Q's are R's. But that means that the P circle has to be inside of the R circle too. So all P's are R's. Okay, so now remember, all P's or Q's is the same as saying if P, then Q. And all Q's or R's is the same as saying if Q happens, then R happens. And then the last statement, all P's or R's, is therefore if P happens, then R has to happen. So as an example, let's say that the first statement is if you are a BC student, then you study math. And the second statement is if you study math, then you get headaches. So there's a kind of chain reaction here. The BC students fall into the studying math category, and then the studying math students fall into the getting a headache stories. So that means that if you're a BC student, you automatically know that you're going to get a headache. It's a chain reaction. I like to visualize it like this. So we know that we have if P then Q, so P arrow Q, and we have if Q happens then R. So if you put these two statements together, we get a chain of events, a chain reaction. So therefore, P ultimately causes R to happen. And you can do this with multiple if-then statements. It doesn't have to just be three of them. So there's actually an error in this example. It says that Lewis Carroll created this logic puzzle, but I changed the logic puzzle. He created many logic puzzles, and we're going to see one in the next example. But I wanted to start with something a little simpler. So I took one of his logic puzzles and I adjusted it. So I guess I could say use reasoning by transitivity to analyze the following Lewis Carroll like logic puzzle and find a valid conclusion that uses all of the premises. Okay, so let me explain. The key to solving by transitivity is to get all of the statements in if-then form, and then write what they're equivalent to using the contrapositive. So I am going to first write the if-then form of each of those statements. And then next to it, I am going to write the contrapositive of it, which I know to be equivalent. All right, so to get the if-then form, you may need to refer to that little chart that we talked about many times that will be provided on the test. What did I do with it? Let's see. Sorry for the scrolling. This chart, okay, to take any forms you may be given and rewrite them in if-then form. So the important thing being that the hypothesis and conclusion are consistent for each statement. So for example, this first one's a little tricky. No kitten is unteachable. We don't have a form in our table that fits no kitten is unteachable, but we do have a form that fits all. So we're going to change this. Instead of saying no kitten is unteachable, wouldn't that mean that all kittens are teachable? And that is in our table. This would be the P being a kitten and the Q would be being teachable. So I'm not going to write lengthy wording to make things flow because we don't really need that at this phase of solving a logic puzzle. What we need is just to know the chain reaction. So I'm just going to say if kitten, then teachable. Okay. And then we're going to move on to the next one. All dogs will play with a gorilla. Well, we know all are keeps the order of the hypothesis, then conclusion. So being a dog is the hypothesis, and playing with gorillas is the conclusion. So I'm going to say if dog, then play with gorilla. Please forgive the grammar. Okay, and that's just to keep things shorter. Animals that play with gorillas are not teachable. So if you throw the word all in here, doesn't that really mean the same thing? All animals that play with gorillas are not teachable. It's implied. If you say animals that play with gorillas are not teachable, then you're implying all the animals, right? So it's still an all statement. So in other words, if you are an animal who plays with gorillas, I'm just going to put if play with gorilla, then you are not teachable. Let me move this little line over here. Not teachable. Okay, that's step one, the if-then versions of each of the statements. Now remember, these are our premises. These are the things we're assuming to be true. But if these premises are true, then their contrapositives are also true because their contrapositives are equivalent. Now remember, contrapositive, we just learned that we switch the order and we negate each component. So instead of if you're a kitten, then you're teachable, we're going to switch the order. So we're going to have in the if part, we're going to have the teachable, but we have to negate it. So if not teachable, then not a kitten. Okay, now the next one, same thing. We're going to take the conditional, if you're a dog, then you play with gorillas. We're going to turn it around and negate each component. So if you're not playing with gorillas, then you're not a dog. Okay, and then that would be equivalent to the original conditional. Now let's look at the third premise. If you play with gorillas, then you're not teachable. So we're going to switch that around. If we need the teachable part first, but not teachable is the opposite of teachable. So we're changing it to, in this case, teachable. So if you're teachable, then, and we want to say you don't play with gorillas. Not play with gorillas. I know it sounds silly. Okay. So now we're going to just pick any one of these facts, because remember, we're assuming these facts all to be true, and we're trying to draw a conclusion using all of the facts. So let's start with this one. If, and by the way, sometimes what the one you pick with might not be the one you pick to start with might not be a good one to start with. So you won't be able to do a whole chain reaction using all three of the premises, but oftentimes it'll work out. If it doesn't, you'll run into a roadblock and you'll start over with one of the other statements. All right, so we have if you're a kitten, then you're teachable. So kitten leads to teachable. Okay, we've already used this, so we're not going to use the contrapositive because that fact has already been used. So out of the other two facts, which one starts with teachable? So I see here on the third fact, if teachable, then you don't play with gorillas. Okay, so that means that teachable leads to not playing with gorillas. So that uses, let me number these actually. So we used fact number 1 to get this arrow here. And now we're using fact number 3, actually it's contrapositive, but still fact number 3 to get, to get this arrow here. And now we want to see, okay, we're done with fact number 3. Can we use fact number 2 to tag on an extra layer to this chain reaction? If we can, then we're done. If we can't, then we'll try starting with a different sentence. So fact number 2, does it show anything about what happens if you don't play with gorillas? Yes. On the contrapositive version, it says, if I don't play with gorillas, then I'm not a dog. So according to fact number 2, if you're not playing with gorillas, then you're not a dog. So we were able to make a 3-statement chain reaction. And then all you do to write your conclusion is start with kitten and conclude with the last statement, not a dog, the last component. So if it is a kitten, then it is not a dog, would be the solution to this logic puzzle. And by the way, we're going to have a learning activity about solving logic puzzles, so that'll be fun. Okay, so you're gonna do your turn number 3. Remember, I recommend that you pause the video instead of just viewing this as an example. You can just give it a shot, see if you can work it. Remember that this chart is available so that you can rewrite any statements in if-then form. It's helpful. Okay, so you know what's the hypothesis and what's the conclusion. I want to remind you that this is a multi-step process. So first you're going to change each of these statements to if-then form. And then you're going to find the contrapositive. And then you're going to make a chain reaction. So pause the video, give it a shot, and then push play when you're ready to see if you got it right. You will get a lot more out of this video that way. Okay, so I'm going to zoom in here and we're going to work on this guy. So we're starting with writing each statement in if-then form. All babies are, by the way, this really is a Lewis Carroll logic puzzle. All babies are illogical. Okay, so this is the same as saying, remember, all P's are Q's. So if P, then Q. So if you're a baby, then you are illogical. Okay. Okay, now nobody is despised who can manage a crocodile. So what are we saying about people who can manage a crocodile? We're saying if you can manage a crocodile, then you're not despised, or if you're not despised, then you can manage a crocodile. Which one seems equivalent? I would say this is guaranteeing that you won't be despised if you can manage a crocodile. Let's write that down. You won't be despised if you can manage a crocodile. Okay, so you won't be despised if you can manage crocs. I find it easier to think of it in those terms. That way I see the if is in the middle. So we're saying if you manage crocs, then you are not despised, to put it in if-then form. And then illogical people are despised. Well, this is the same as saying all illogical people are despised. So that's again an all statement. Being illogical persons causes you to be despised. So if illogical, then despised. All right, so that's the first phase, but we also need to include the contrapositive version because we might need it to make our chain reaction, as we saw in the previous example. So if baby then illogical, remember contrapositive, we have to both change the order and negate the component. So we know the illogical part's going to be at the beginning, but we would say if not illogical, or you could say if logical, and that would be fine. But I'm just going to stick with if not illogical, then you're not a baby. Same thing for the second one. So instead of if you manage Crocs, then you're not despised, we need if not despised. So if despised, then it must mean that you can't manage the Crocs. And then the last one, if you're illogical, then you're despised. So if you're not despised, changing both the order and the negation, then you are not illogical. Okay, now we're going to pick a statement to begin with. I just usually pick the top one. If you're a baby, then you're illogical. So we have baby. Let's number these 1, 2, 3 so we can talk about it. So baby causes you to be illogical. That's premise number 1 that we use there. Then we're looking for something that starts with if illogical. Well, statement 3 does. If illogical, then despised. So in statement 3, we get from illogical to despised. And then we're looking for something that starts with despised. In statement 2, if you're despised, then you can't manage a crocodile. So despised means can't manage Crocs. Oops. Okay, so that came from statement 2. So now we've used all 3 of the premises, and now to write our solution to the logic puzzle, our valid conclusion that uses all of the statements, we need to say that if you're a baby, then you can't manage crocodiles. If you are a baby, or if it is a baby, however you want to say it, then you can't manage crocodiles. Okay, now it is possible, please note, that this statement that you get is also equivalent to its own contrapositive. And had someone started with statement 2 instead of statement 1, you might have ended up with a different version that's equivalent. You might have ended up with if you can manage crocodiles, then you are not a baby. And that would have been fine as well. Now, the reason I want to emphasize this is because we are taking in my class multiple choice tests. So let's say that the answer that you're supposed to choose is if you are a baby, then you can't manage crocodiles. But you get if you can manage crocodiles, then you're not a baby. You need to recognize it's equivalent to this because it's contrapositive and choose the right answer. So please be aware of that. Okay, so that's everything. I hope you found this video helpful. If you did, please give it a thumbs up. That helps other students to find the video. You can also subscribe to my channel, Miss Hearn Mathematics, for more math videos.